You understand? So 18 after 19 would be 37, right? And so then if we take 37, right? It's 37, then that means I get up to 37.59, understand? If you're getting up to 18.59. No, I'm not getting up to 18. You're getting up to what, 18.30? And then if it's 18.31, oh, okay, then we can stick with that. Yeah. Okay.
All right, so we have screen recording going on. Ooh.
Yeah.
And we got about 30 seconds before noon time. Today it feels like San Francisco, especially the west side of San Francisco. I kind of miss the kind of cold temperature and the drizzling, and it's all year round. You can have sunshine and all the good stuff, you know, on the east side of San Francisco, you know, like in around the bay part, the bay side. But on the Pacific coast side, it's always like, and super windy. I kind of like it. You go down to the beach and your face will get sand blasted. That's why people from San Francisco have such smooth skin, because they get sand blasted all the time. All right, well, it is time, so I'm going to get started here. So what we'll do today is to use this graph as an example, and then we'll just go ahead and follow the Dijkstra's algorithm that we started to talk about last time. So what we'll do today is quickly go over, you know, what it means, what it is really trying to do, and then we'll use this as an example. I got a spreadsheet prepared as well. Okay, so when it's time, we'll transition to the spreadsheet, which you can view as well. So if you have a laptop computer, especially for those of you who are doing this remotely and you're home, you have a larger screen, you can look at both the Zoom screen and also look at the spreadsheet at the same time. I think that might be helpful. If you have your own laptop computer, you also might want to open up the algorithm on the side as well. So this way you can look at the graph, you know, the graphical one, you can look at the trace, and you can look at the algorithm all at the same time. And I think that will help you really kind of not only to understand the concept, but to also connect, you know, how it works, you know, by using a trace. All right, so as I said a little earlier, we'll go back and kind of revisit the algorithm just a little bit. Once I have to, first I have to find it first. So I'm not exactly sure where to put it. There you go. All right, so this is the Dijkstra's algorithm. We'll go over the entire algorithm first, and then we'll go for the trace. So the algorithm, you know, starts with some initialization. Let me highlight which parts are the initialization. So everything from here all the way up to right before the while loop, these are all initialization. We are basically just doing this one-shot thing so that we can get the whole thing set up. The input to the algorithm, which basically are the parameters to the algorithm, include G is B. In other words, we are using a set of vertices and also a set of edges to represent a graph, and it is directed. So that's why the edges is a set of two tuples, because the ordering is important. We have a D function. The D function maps edges to non-negative real numbers as quote unquote the distances between the points here, or the distance of a particular edge. We have the set S here, which is the subset of vertices that are designated as destinations. In other words, we want to find the shortest path from every single vertex to the quote unquote closest destination. So those are the destinations. It is a subset of V. And then the way we do the initialization is the L function applied to a destination vertex is going to be 0. Because L of V is basically indicating the length of the shortest known path to a vertex, to a destination vertex. So that means, if the vertex itself is a destination, the length of the shortest path to a destination would be 0 because you are already standing on a destination. Question?
The vertices include the not destinations.
It includes everything, includes both the non-destination and the destination vertices. So the destination vertices is a subset of all vertices. It'll be clear when we go over the example. So for what about the rest? In other words, what if we are dealing with a vertex that is not a destination? Then L of V is initialized to be infinity or the largest number that you can store in that particular function. Because unless we find a path, we're going to assume that this particular vertex does not even connect to a destination vertex, and we'll try to connect it as the algorithm progresses. And that's why L of a non-destination vertex is going to be infinity. So let me just kind of pause up to this point and see if there are any questions. We are now done with explaining the first 4 bullets of the algorithm. Are we good so far? If you're online, please use your voice to ask questions because I cannot really watch the chat, the text chat. All right, so we do not seem to have any questions. Then we'll continue. So now we are going to have a set Q. It is initialized to the set S. So everything in S is now in Q. We also initialize a set E prime. And this is initialized to an empty set. E prime is really the result of the whole thing. In other words, after the entire algorithm completes, then E prime will contain a subgraph of the original graph, and those vertices will basically indicate the shortest path from every vertex to a destination. So this modified Dijkstra's algorithm does not only find a shortest path between a vertex and a destination, it allows you to specify as many destination vertices as you want, as you need, and it will find the shortest path between every vertex and the closest destination vertex. So it's kind of cool, okay? But the modification to the original Dijkstra's algorithm is actually really simple. So it's not even deserving that I add my last name to the name of the algorithm. I'll just put it quite simply at that. All right, so are there any questions before we get into the actual logic of the algorithm? Nope, okay. Has CISP440 gotten into Dijkstra's algorithm yet? Is he planning to? Is he in the syllabus? Okay.
It's like the very last thing.
Okay. Okay, that's okay, but we can learn how to do this one by hand first. I think the one he is covering is only using a single start vertex and a single destination vertex. So you can kind of look at this one as a quote unquote more general version of the of that other algorithm. This algorithm, if you implement it in JavaScript, is actually pretty easy because JavaScript already has the concept of the data structure of a set. So that means all the set operations is like easy to do. But if you do this in C++, I think it will still be pretty easy. You can use a template class. You can use the set template class. Generally speaking, I do not like template classes. I go like this on standard template classes because once you use a particular template class, it just brings in the whole kitchen, the kitchen sink, and so on and so forth. It is not lean at all. All right, so we're going to get into the logic. The logic is a little lengthy, but that's only because I include a lot of explanation along the way. So if you just focus on the code itself, it is pretty simple. But if I just list the code, it becomes difficult to understand. So that's why I put in comments as well. And that's kind of what makes it kind of long. All right, so the first one is the first action that we perform in the loop is we select a vertex V from Q. such that V has the least L value. Basically, that's what it's asking, because it's the quantified statement is saying everybody else has at least as much of an L value as vertex V. So that means V is the one that has the least L value of all the vertices in Q. Are we understanding that part okay? Because that was one of the last thing that I explained on last Wednesday. Okay, so this paragraph here, okay, is also why the algorithm is also called a quote unquote greedy algorithm, which I kind of do not agree. I don't think that's a good description, but in the analysis of algorithms, this approach is basically coined or called a greedy algorithm. The next thing we do is we remove the chosen vertex V from Q, because we are now saying, okay, let's go ahead and take a look at this one. We are taking it out of Q because Q is basically a bunch of vertices that we need to look at. So the moment we have chosen V to look at, it should not be in the set Q anymore. So we are removing that from the set Q. This is the operation to do it. We cannot just say uppercase Q minus V without the curly braces, because the subtraction here is a set operation. It requires both sides to be sets. Okay, so that's why we need to create what we call a singleton set that only has one single element in order to use the operator that we have already talked about from week 1. Okay, so that's why the final exam is called how did I call it? Unintentionally comprehensive, which basically means the operators from all the way back to week 1 may still be referred to and used in the final exam. All right, so we have a nested loop here, okay, because the nested loop is looking at all the incoming edges to vertex V and say, okay, so we know vertex V has a really short path to a destination. So let's take a look at all the other vertices that are incoming to this promising vertex, because we might be able to find the shortest path for all of those other vertices that connect to vertex V as well. So that is the idea. That's the idea of why we are looking at all the incoming edges to vertex V. And this is really just the set notation to express the same thing. So we're including in this particular set here, those are all the incoming edges to vertex V, which means vertex V is the second item of the tuple corresponding to each edge, which is exactly what this is saying here. See how nice mathematical notation is, because it takes me so many words to describe basically the same thing in, a set notation. So this next part here is just giving the edge a name by itself. It is called E. E is now a variable in the algorithm. So this part is important, okay? Because it is a comparison, and it looks like as a part of the action. This is significant. So the question is, what kind of a condition is this? Why is it important? So the way we look at this is we look at the left-hand side of the comparison, L of D plus D of V. But what does that mean, right? Well, the first thing is we need to look at what is L of V. What does L of V represent? Yep. Is the length of the shortest known path from vertex V to a destination. Yeah, because we can have multiple destinations, but it is the one that is the shortest. It's the length of the shortest path to a destination. Okay. And what is D of E? D of E is the distance of the edge that we're looking at. So by combining the known shortest path from vertex V to a destination and the edge that is connecting W to V, we might have found a shorter path for vertex W. Does that make sense? Because vertex W connects to V, vertex V has a path to a destination. So we might have discovered a shorter path from W all the way to a destination at this point. Does that make sense? So the entire left-hand side of the comparison is the length of a path from W all the way to a destination. Is that okay? What are we comparing it to? What is on the right-hand side of the comparison? What is L of W? Well, since you already know what is L of V, L of W is kind of the same thing, but it applies to vertex W, which is the length of the shortest path from W to a destination. In other words, we are trying to determine, did we just find a shorter path than what we had discovered up to this point? That's what it's asking. So if the answer is yes, okay, if L of V plus D of E is indeed less than L of W, then we go like, woohoo, we just found a shorter path from vertex W to a destination. All right. And just as a suggestion, noting the time of where we are now may be important, because this really is the key point of Dijkstra's algorithm. How do we know that we have just found a shorter path? All right, so what if we do? Well, if we do, we just have a few bookkeeping things that we have to kind of keep track of. The first thing is we have to remember, oh, we just found a shorter path. So the old L of W value is no longer representing the length of the shortest path from W to a destination. So we just have to update it. No big deal. But what we have put into E prime as a solution before is no longer a solution. In other words, if there are any edges from W to a particular vertex, that edge is no longer an edge of the shortest path from W to a destination, because guess what? We just found a shorter one through vertex V. So we are removing all the edges in E prime where it starts from vertex W. We're erasing, okay? We're basically looking at the old shortest path and go like, oh, that doesn't work. Let's erase that edge, okay? So that's the second bullet point you'll ask in the then of the conditional statement. And then the third bullet point is say, okay, now that we have erased the edge that is not representative of the shortest path, let's add the edge that is on the shortest path, at least up to this point of running this algorithm. That's the third bullet point in the then statement. And then the fourth bullet point of the then statement is also important because it is adding W to the set Q. In other words, hey, we just found a shorter path for W to get to a destination. Maybe we should consider all the incoming edges of W because we might discover that one of those would have found a shorter path at this point as well. So that's why we're adding the vertex W to the set Q so that it would be considered, or at least it would be part of the consideration of should we take a look at this one because it might all the incoming edges to this particular vertex may help other vertices to find a shorter path. So is that okay so far? Yep.
So E starts out empty.
E prime.
E prime starts out empty. Then you go through the algorithm. Then you reach the where you replace it.
Because yeah, so this part erases the edges that do not work, and then this part adds the vertices that do work.
And then you're updating it to W, and you're reusing the W defines it. Yeah.
Because we just found a shorter path for W. So all the vertices that connect to W may find a shorter path as a result as well. Does that make sense?
I think it. I understand it. It was like a visual.
Okay, well, we'll run an example. That's why I plan to kind of give you guys a trace with a real example, and I even prepare an actual graph so that you can visually see it. Are we ready to move on? This is just a really dry and abstract description of the algorithm. But once we go through the example, it's a lengthier example than usual because I used to have shorter examples. But I think this one will help to really help you understand, how you can discover a path and then later on go like, oh, that's not a good one. Let's try this one. Oh, that's not a good one either. Let's try this one. That is not a good one either. Let's try this one. Okay, so that graph is designed to show you that you can try to trick Dijkstra's algorithm, but it will always find the shortest path. Are we ready to move on? Are we excited to move on? Maybe not. Alrighty. Let's move on then. All right. So I'm just, tracking the other side. Okay, so we got people already attending remotely. All right, so if you are doing this online, you are at a slight advantage here because you can keep this algorithm on your screen. And then what I will do is I'm gonna switch between a few things. So the other thing I want to do is to show you the actual graph, that is kind of in a graphical way. This is the graph, and you might notice that some vertices are round or in circles, in bubbles, and then other ones are in squares. The one in squares are the destinations. So we have two destinations. Vertex E is a destination, and so is vertex F. Those are both destinations. And I do apologize that I reused the name E because we have the local variable E in the algorithm. So this is representing vertex E and not the variable E in the algorithm. And once again, D is also the name of the distance function. But in this case, it is the vertex D and not the distance function D. Yes?
Path 2, that's just the cursor, not like an arrow of any significance, right?
Path. Oh, the label 2?
No, path 2, going from D to F, that's just the cursor.
E
Oh,
to F. You mean this 2?
Yeah.
He understands.
That's the distance, right? Yeah, that is the distance. And for those of you who are curious of, how long did I spend to actually make this graph? The answer is not long, because this is the actual markdown representation on the left-hand side. It has a language called Mermaid, which allows me to draw graphs, in a very easy way. It has a lot of flexibility too. If you want to use the diamonds and the parallelogram in the flowchart, it has all of those. And it automatically formats too. It automatically choose the best way to represent a graph. So I don't even have to bother with, I need to rearrange it like this so that it looks better. It does it automatically. Coincidentally, in case you are already looking into Markdown, Mermaid can also represent Gantt charts, lane charts in the UML, and many other professional charts that you might encounter in your computer science endeavor. So, just things that you might want to keep in your mind if you ever need to draw graphs and you don't want to kind of do it manually. It's a really cool way to do it. All right, so what I'll do is I am going to take a snapshot of this, kind of a smaller version of this. Give me a second here so that I can take a snapshot so I can show this along with the algorithm. So this way it's easier for you guys to kind of keep track of which vertex and where is it going. That makes it super easy. So we'll make sure that this one is always on top. So this way we are not going to lose this little diagram as we go through the trace. All right, so now we are ready to actually start the trace, which I have prepared here. And so no one has signed into this one. All right, so this is in the shared folder of CISP440. The link to the shared folder is at the top of all the Canvas modules. So if you are at home, if you're remote, or if you have your own computer in the class, you can choose whether to track the tracing or not, okay? I would do my best to kind of make sure that, we keep everything in context. But one thing I cannot do is to show the algorithm and also show the trace at the same time. That's just going to get really confusing because there's not enough space on this screen to do both. Yes, I do have two screens, but that means I have to use Windows and also Linux and two keyboards at the same time. I think this is a little bit easier to deal with for me. All right. So what we're going to do, we do the initialization, right? So let's go ahead and do the initialization, which mostly has to do with L. So the L value of A should be what? Do you guys remember from the algorithm, how do we initialize vertices depending on whether it is a destination or not? Which two are our destinations? Let's start with those two. E and F, and what should be those L values be? What is the L value representing? the length of the shortest path from that vertex to a destination. So if E and F are destinations already, what should be their L values? Zeros, very good. Okay, nice. And what about the rest? Infinities, yes. So now we just, let me see if I can put infinity as a symbol. I cannot remember how to do it. There's a way to insert a symbol, but I cannot remember how to do it. I'm just gonna do this. I'm lazy. There we go. Okay, so those are all infinities. The E prime is initialized to an empty set like so. And then Q is initialized to be the set of S, and what would that be? So initially, what would Q be? With two vertices should be in Q as a set, according to the initialization. E and F, that is correct. Good job. There we go. So that's our initial condition. And what we'll do next is, oh, I just made a mistake here. I do apologize, but now I have to figure out how to fix that mistake, because there's a way for me to track the current values of everything, so I don't have to scroll and lose track of the current values. So let me do this. I do apologize that I have to kind of pull something like this, but it is necessary to improve the readability of these equations here. Okay. All right, so this is from A4. Okay, that's good. And then we copy these or cut and paste over. There we go. All right, so let me explain what is row 3 and what is row 4, because they look identical, but they are not. Row 3 is representing what do we have at this point of the algorithm. In other words, it is updated dynamically. Row 4, on the other hand, is really the result of the initialization. So as the algorithm progresses and we start to adjust the L value and change the value of Q and so on, row 3 will always update. So this way, I can scroll the bottom part of the spreadsheet and still be able to track the values of Q and all the L values and also E prime. Is that okay? We'll see it. Okay, this is kind of a little bit of a spreadsheet trick that I do in this case. All right, so row 4 is representing the initialization. So now we can go into the algorithm, and unfortunately, do you guys want me to kind of switch between the algorithm and the trace in class? Would that be okay? Okay, I can certainly do that, because it can be a little bit confusing if, let me move the correct module here first. So where is it? Which module? There we go. Okay, so I'm just placing the module right next to the spreadsheet. So this way it's easier for me to kind of switch between those two. All right, so now we are done with the initialization. The first question is, are we done yet? Can we just get out of the loop? Well, we can only get out of the loop when Q is empty. Okay, when Q is empty, the condition is false, and only then we can get out of the loop. Okay, so let me practice my shortcut key here. Does Q look empty to you? Just look at row 3. That's the current state of Q. Nope. Okay, so we cannot exit the loop, the while loop. So that means we have to, we have to continue with the loop. So now we have to find a vertex V so that it has the least value amongst all the vertices of Q. That's what we need to do. So which one would you choose? Which one has, quote unquote, the least value between E and F? Exactly, like, is that a trick question? Because they are both zeros, right? So in that case, you can choose either one, because the requirement is it only has to be less than or equal to everybody else. So that means, hey, if they are the same, just take your pick, okay? Flip a coin. But in this case, it has nothing to do with binomial distribution. It simply means it really does not matter which one we want to choose. Okay, so I'm gonna let you guys vote on which one you want to choose. Which one is more interesting? I think I'm gonna choose F, okay? Because it looks like everybody goes to F directly. And just look at the graph. Look at the graph here. This is a destination, E goes to F, D goes to F, C goes to F, B goes to F, and A goes to F2. Maybe we'll just be done with one single loop on the outer loop. Okay. All right, so we're going to do that. Okay, so vertex F is the vertex in Q that we are choosing, and it's going to be in the variable V in this case. Okay, so we'll put F over here, which also means we need to adjust Q, because Q is we have to. Okay, let me switch to the algorithm, because we have to remove vertex V from Q as the second step. So that's what we are doing. There we go. All right. So this is the magic that I was referring to. Column 3 is reflecting the current state of the important columns. So this way, as we scroll through the whole thing, we'll still be able to keep track of Q and all the L values, easily. So you might be asking, but why not V and E? Because V and E are local. Okay, the use of variable E, local variable V and E are very localized. So there's no need for me to kind of have to track their current value all the time. All right, so what do we do next? Well, we kind of have to look at the edges. Okay, what incoming edges do we have for vertex F? So corresponding to the algorithm, I'll do this a few more times and then we'll stick with just the trace. Okay, so now we are at this point here for each edge, so that the edge is ending at vertex V, which in this case is vertex F, do the following. Okay, so that's what we're trying to do here. And so which one do you guys want to consider first? I mean, it doesn't really matter which one first, but go ahead, tell me. Let's pick C. Okay, so now we are considering edge CF. Okay, so what do we need to do next? Let's go back to the algorithm. So we'll do the back and forth a few more times, and then when we get familiarized, then we'll stop doing that. So now we are done with this bullet point. The next step is really just to do the comparison. What is L of V plus D of E? Is it less than L of W? Okay, so we'll kind of track that in our mind and then switch back to the trace. What do you think? If you just look at the diagram, what is L of V? V is F, so L of V is going to be L of F over here, which is a 0. Okay. What is D of CF? D of CF is right here. It is a 4. So on the left-hand side of the comparison, we have 0 plus 4, which is a 4. On the right-hand side, we have L of W. W is referring to the beginning of the edge, which is in this case C. So we are really looking at L of C. What is L of C at this point? L of C is infinity. So the question really boils down to, is 4 less than infinity? Okay, so that means we have to go into the conditional statement or the then branch of the conditional statement. So we'll go take a quick look at what we need to do in that case. So there we go. All right, first thing is to update L of W to be the left-hand side of the comparison, which we already know is 4. Okay, so we'll go ahead and do that. So now we update L of C to be 4. That's not working. Why is it not working? Let's see. I'm debugging my spreadsheet here. Just give me a second. So it's 3 plus count. Oh, it's not count because we need to find the last one that has a value. So count doesn't work. All right. So we have to find the last one. I'm trying to figure out in the spreadsheet, how do we figure out which cell or has a value, which last cell of a column has a value. Okay, so give me a second here because I need to look this up because I really want to find out how to do this. So we're looking at Google Sheets count if multiple criteria. Okay, find cost. So,
Check count if,
hmm?
in check count if, compare the columns, which one has. the value?
Well, they may not have the same, so we'll take a quick look at this solution. If NA get the last number in the column. So we're looking for something that is not a null, but we want to find the last one. That's the difficult part. Well, I suppose I can just do it manually first, and then we'll go back and fix that later. All right. I was kind of hoping that we can do this without having to do this manually, but that's okay. We'll go ahead and do it like so. All right, so I'm just doing this manually right now. You know, it's kind of lame, but I don't want to waste class time to figure out, how to do this in a more elegant way. All right, so the next thing we need to do is to remove all the edges in E prime that start with vertex C. Do you see anything in E prime that starts with vertex C? What is E prime right now? It's an empty set. So there's nothing, right? Okay, well, that means I don't have to do a single thing. It is still an empty set. And then right after that, the next operation is to add the new vertex to it. And the browser is stuck. The computer is not stuck. It's just the browser. All right. No, it's not stuck anymore. There we go. So we just did this part here. There's nothing to remove because we do not have any edges in E prime yet. So now we're going to add the edge that we were looking at, which is from C to F into E prime. So we're doing a union. So now we go back here and say, okay, well, we need to update it to CF as the only single element here. And then I have to do this by hand for now. I'll figure out a way to do this later on. All right, and there's one more thing to do. What is the last thing? I'm not going to say it, but I will let you guys think about it. See if you can still remember the last thing that we need to do in the then branch. We just found a shorter path for one of the vertices, in this case, vertex C. So what is the last thing that we have to do? Update vertex, update set Q. That's right. Okay, so every time we update the L value of someone, that someone needs to be added to the set Q. And since this is a set, the ordering does not matter. All right, so that completes the first iteration through the for loop. And let me switch back to the algorithm here. So now we are at the very end of the conditional statement, and we have only gone through the first iteration of the for loop, and we are also in the first iteration of the while loop. Are we okay so far? Okay. So have we considered all the edges, ending at vertex F? You look at vertex F here and go like, not by a long shot, because all we have done is to look at the edge CF. There are 4 other ones that we have to look at. So now we switch back to the spreadsheet, and then we go like, okay, which one do you want to evaluate next? Pick one. We got A, F, B, F, D, F, and E, F left to consider. AF, okay, we'll choose AF. So now the question is, did we just find a shorter path from vertex A to a destination? According to the L value of A, yes, we did. Okay, because the L value of A is currently infinity. The new path would have a length of 11. 11 is not short, but it is still less than infinity. So we go into the conditional statement again, and then we just do everything that I mentioned earlier, except this time we're doing it to the vertex AF and the vertex A. So the first thing we need to do is to update the L value and say, okay, vertex A, you just found yourself a shorter path. Instead of having no path at all, we now have a path to a destination, and the length is 11. And then we just go here and say, let's add that edge to the set E prime. So AF is now in E prime. And then we also have to remember to add A into this set here, like so. And I'm going to just copy and paste stuff here. Oops, nope, not you. Copy, paste. All right. Are we doing okay so far? That's with AF. So what other edge, what other incoming edges do you want to consider? What is the next one? We've got 3 left. B, okay, BF, okay. So now we're looking at BF. And then we repeat the same questions. Did we just find a shorter path from vertex B to a destination? According to the L value, yes, because before we did not have any path, okay, from vertex B to a destination. Now we have one, so it has a length of 5. So we update the L value to 5 first. Okay, change this one too. And then we have to add the edge into E prime. So E prime is now all of this plus BF. And then we also have to remember to add B to the set Q, like so. We got 1 edge left, right? Two edges left. So we got A, B, C. So which one do you want to do first, E or D? D, okay, let's do D first. D is easier. E is a little bit interesting. So we'll do D first. And then the question is, did we just find a shorter path from vertex D to a destination? According to the L value, yes, okay, because we didn't know any path before. It has an L value of infinity. Now we found one. It has a length of 2. And then we have to remember to add that edge to E prime. So E prime now includes DF, there you go. And then we also have to remember to add vertex D to the set Q. So Control C, Control V, and then just add that one extra one here. That would be D, right? Okay. And we have one more edge, right? Because you can see that there is an edge from E to F. And somebody's going to say, but Tag, E is a destination already. So should we take that into consideration and just say that it's special because it's already a destination and we should not do anything differently? The answer is no. Okay. We apply the algorithm as it is described, which means now we look at we reevaluate this condition here. We look at L of E, and then we add D of the edge, which is EF. It has a distance of 1. So we have 0 plus 1 on one side, which is just 1. And then we look at L of W. L of W in this case is L of E, which is 0. So in other words, we're asking, is 1 less than 0? The answer is no. So that means, oh, I don't have to do anything over here. Is that okay? In other words, from the perspective of the trace, we do have to indicate that we consider the edge, but there's nothing that we are doing here because we are not getting into the then branch. Is that okay? Yep.
Okay, so in that case, it is kind of like filtering itself out since it's already a destination. So we are I didn't treat it differently.
We are not treating it differently from the perspective of, is there a special consideration of whether a vertex is in as a destination? Nope. Once we initialize, Q to be the set of all the destination vertices, the rest of the algorithm does not make any distinction of whether a vertex is a destination or not. Okay, and that's the kind of code that you want to write in general, which means you don't want to have special conditions all over the place. You want to make it as general as possible. All right, so we are now done with the for loop. So that means we are now ready to go back to the beginning of the loop, and we ask, are we done? Is Q empty? Let's check. We go like, no, we are not quite done yet. Q now has 5 elements. So that means, oh, fine, we have to go through another while iteration. So what do we do in the next while iteration? The first thing is we have to find a vertex within Q such that that vertex has the least L value. Okay, so let's see which one we should choose. So now we have A, B, C, D, E as vertices in set Q. So we now look at those values. Oh, I forgot to update one of those. There we go. So now we look at these 5 values and say, okay, who has the least value? What do you think? Vertex E. Okay, so we now choose vertex E as V. And now we have to look at all the incoming edges to vertex E. You look at vertex E here and go like, okay, it has got 2 incoming vertices. We got A, E, and we also got D, E over here. Okay, so the ordering of which edge we evaluate first in the for each loop does not matter. So you guys can say, which one do you want to evaluate first? A, okay, so we'll evaluate A, E first. Oops, A, E. All right, so did we just find a shorter path? Because the length of the shortest path we have discovered so far is 11. And now we have a path of 10. I think we got a shorter path. Yes? So what do we do when we find a shorter path to a vertex? We got a bunch of stuff to update, right? So we have to update L first, because remember, the L value is really just tracking the length of the shortest path discovered up to this point. Okay, so we got to keep it up to date. So it is now 10, and I have to manually update this one too. And then this time, we do have something to do with E prime, because we do have something that starts with A already, meaning our AF. So AF technically is removed first. Then we add the new edge that is leading us to the destination with a shorter path. So that would be AE. So now we are deleting AF, and then we're adding AE to the set E prime. And we have to add E back, we have to add A back into the set. I forgot one thing, because once we chose E, it should not be in the set anymore. So E cap D is what it should be. And we have to add vertex A to the set, but that really does not change how it looks like, because it is already in the set Q. Yep.
The distance from A to F was 11. That was a different thing. Now we're looking at A to E is a different destination, and that was 11 was from A to F. So
Yes.
are they different things?
Nope, they're the same thing, because if a little boy wants to go to a bathroom, do you care which one?
Also, they're both the same destination, and we don't care which one we arrive, but we just care about which one is closer.
Okay, you have to keep in mind the Six Flags, scenario that we talked about last Wednesday. You are a chaperone, with a bunch of 6-year-olds, to the theme park. And if one is going like, I need to go to the bathroom, do you care which one you're going to? It's like, okay, we are right next to a bathroom, go to this one, but I don't want to go to this one. I want the next, next to the gift store, gift shop. No, you're going to this one. All right. So next, we have another edge, right? We have another incoming edge, which is DE. Okay, so we look at DE here. And then we ask, did we just find a shorter path from D to E? The answer is yeah, because the length of the shortest path before has a length of 2. But this time, when you look at the edge from D to E, It only has a distance of 1. So yes, we found a shorter path again. Woohoo! Okay, so we changed the 2 to a 1 and make sure we double update on the top. Oh, I forgot to kind of update this one too. So you can see why I really want to have a spreadsheet solution to do this, but I don't want to do the research here when we are doing the trace. Okay, so we copy and paste this. And this time we have to erase DF first because DF is no longer an edge on the shortest path, So now we have to add the actual edge of the shortest path, which is DE. And then we also have to remember to add vertex D to the set, but set Q already has D in it, so it doesn't seem that we are making any changes in this case. Are we good so far? All right. So we are now done with the for each loop again, okay, in the second iteration of the for loop. And now we are getting back to the beginning of the for loop and looking at this and go like, we are not done yet. But which one should I choose this time? We only have A, B, C, D left. In other words, these are the 4 values that we are evaluating, and we need to find the one that is the smallest. Which vertex has the least L value? Vertex D, okay, so we choose D here, and then we remove D from the set, okay, so most of the time I forget to do this part, okay, just because that's just me. So there we go. And now we have to look at all the incoming edges to vertex D. There are 2. So there's one incoming edge right here and one incoming edge right here. You guys can choose which one we want to evaluate first. A, okay, so AD is the first one to evaluate. And are we finding a shorter path? In other words, the length of the shortest path up to this point has a length of 10. Okay, the length of the shortest path is 10. Are we discovering a shorter path if A is going through D to get to a destination? Okay, so what is the length of this new path that is shorter? 5, okay. So we now say, we found something shorter, 5, and update this one over here. And now we have to go to E prime and say, that path that we found earlier is not really the best. We just found a shorter path from vertex A to the destination. So A has to go to D first, and then D goes to the destination with its own little path. And then we have to add vertex A back to the set, but it already has it. So it would appear that we are not doing anything. But in reality, we did do a union, but it's just that the union did not end up changing anything in this case. Are we still doing okay so far? Okay, so if at any point you're thinking, oh, this is going to be really boring for the rest of this class, then congratulations, you're getting it. Because if you get a sensation, it's like, oh, this is really just mechanically doing the same thing over and over again, that means you're getting it. Okay, so that's a good sign. Not that I really want you guys to fall asleep because of that, but okay, so what do we do now? Are we done with all the incoming edges to D? No, so we've still got CD, right? Okay, so now we have to look at the edge CD, and then we ask, are we finding a shorter path, from vertex C to the destination? So vertex C going through D to a destination here would have a length of 3, but according to our L value, the length of the current shortest path has a length of, the length of the current shortest path is 4. So yes, we just found a shorter path again, right? The length of the shorter path is 3. Does that make sense? Okay, we good? Okay, so you can see how I really constructed this graph to try to trick Dijkstra's algorithm as much as possible. All right, so we found a shorter path from vertex C to a destination, and the new path has a length of 3. So we'll go ahead and update that. And then we also have to look at E prime and say, we got some erasing to do because, whatever edge is coming out of vertex C as the part of the solution, it's not really a part of the solution anymore because that led to a longer path. We now find a shorter path going from C and then to D first, and then to the destination. Yes.
Why is C3?
Why is the L value of C3? Because we have this 2 plus the 1 here. Yeah, they're added. Because L of D is 1, and then D of the edge CD is 2, so 2 plus 1 is 3. 3 is less than what we had before, which was a 4.
So should our previous L value for A be 6 instead of 5, since it was 5 to D and then 1 to E?
That is correct. It should be a 6, not a 5. Because it is a 5 plus the 1. Yep. You're
We gotta
correct.
change the top bar as well.
Thank you. There we go. All right, so now we are done with the for each loop. We go back to the while loop. Oh, one more thing. We have to remember to add C to the set Q. It's already here. So it would appear that it did not change, but we actually tried a union operation already. It's just that it's already there. All right, so now we're down to A, B, and C. Which one has the least L value? C has the 1. Okay, so we're going to take C out of Q. And remember to reflect that over here. And now we look at both incoming edges into vertex C. Which one do we want to look at first? Vertex A, okay, so so we look at AC, and now we are asking if vertex A is to go through vertex C and then go to a destination, what would be the length of that path? Well, we know L of C is a 3 already, and this edge has a distance of 2, so 2 plus 3 is a 5. And then we have to look at L of A and go like, oh, but the previous path, the previous known shortest path has a length of 6. So we just found yet another shorter path from vertex A to a destination. Is that working okay? Which has a length of 5 this time. So we update that and update that over here. And then what else do we have to do? Well, we got some corrections to do because E prime is storing all the edges of the shortest paths. So AD is not really an edge of a shorter path anymore. Instead, it is now from A going to C, like so. And I think I've forgotten to update E prime for a while. So there we go. So now we have to add vertex A to the set, but it has it already. So it would appear that we are not doing anything. Is that okay? All right. So what is the other edge going into vertex C? That would be coming from B. Okay, so let's do that. So now we look at vertex B and go into C. And then we ask you that question again. Are we finding a shorter path from vertex B to a destination? What we had before has a length of 5. What we have now, what we are considering is for vertex B to go through this edge, which has a distance of 1, and then C has its own path to a destination, which is 3. So now we have 1 plus 3 as the length of the new path that we're considering. The old path had a length of 5, so 4 is less than 5, and yet, so we have discovered yet another shorter path for vertex B. Are we doing okay? Yep.
When you considering B, you check both shortest path to F and D at the same time.
Say that one more time.
When you're considering C, so you check both shortest path to F and D at the same time, and then you pick up the shortest one.
Well, the L value is always the length to the length of the shortest path to a destination, which means if there are multiple destinations, it is the length to the one that is closer to the vertex. So that means, we really do not care how many destination vertices there are. The L value is always reflecting the length of the shortest path to the one that is closest to the vertex. So the algorithm automatically make adjustments, if there is a shorter one. If there's a destination that's closer, it will figure it out. Is that okay? All right. So now we have to update this to 4, this also to 4, and then we go, and we have to make another correction because if B going through F to a destination is not the shortest path anymore. we really need to go through C first to get to a destination. And then we have to add B to the set Q, but it's already here. So it would appear that we did not make any changes to set Q. So that concludes the for each loop of yet another iteration of the while loop. And we look at this and go like, man, we are not done yet. Okay, we still have 2 more vertices left in Q. So out of these 2, which one has the shortest path? A shorter path to a destination. Vertex B. So we extract that from set Q. Q only has A left now. And now we have to look at the 2, the 1 incoming edge to vertex B. Okay, finally, there's only 1 single edge, right? So now the question is, are we finding a shorter path from vertex A to the destination? So how do we decide that? We look at L of A, which is a 5, which means the length of the shortest path that we have discovered up to this point from vertex A to destination has a length of 5. So now the question is, if I were to go through B, would I find a shorter path? So the first thing we need to do is to look at L of B, which is a 4. And then the edge from A to B is 1. 1 plus 4 is a 5. So 5 is less than 5 is false. We are not discovering a shorter path. I mean, it's the same, right? 5 versus 5 is the same, but it's not any shorter. So we are not going to do a single thing. We skip over this entire thing. There's nothing to adjust here. We're not updating the L value. We are not changing E prime, and we're not changing Q either. So now we go back to the main loop, the while loop, and we say, ha, we only got 1 thing left. So this has to be vertex B this time, right? So we get it out of the set. The set is now empty, but we are not done yet because this is already in the body of the while loop. So that means we still have to look at all the incoming edges to A, and there's none. So we exit the for each loop, and then we get out to the while loop. It looks at the set Q. It is now empty. Forgot to update the other way up here. So now we are done. Okay, I keep forgetting to update all the things up there. So now we are all done. So this is the trace of running Dijkstra's algorithm. Okay, so now the question is, okay, so are we really finding the shortest paths? Because I'm claiming that this E prime here is giving you the edges that will construct the shortest paths from every vertex to the closest destination. The question is that really the case? Are we sure? So we look at these, individually. Okay, so we'll look at vertex A, and then we ask, is AC and then CD and then DE, is that the shortest path? Oh, that looks like the shortest path to me. 2 plus 2 plus 1 is 5, and no other paths would be shorter than this. There's one that is equal distance, but it's not considered any shorter. Okay, what about vertex B? If I start from vertex B, is the path from B to C, C to D, and then D to E, is that the shortest? 1 plus 2 plus 1, 4 is the length of that path. Is that the shortest? Yep. And then we look at vertex C, same conclusion, vertex E, the same conclusion. We look at vertex E and go like, hey, vertex E is not the first of the 2 tuple here. What is going on? We don't need one. Vertex E is a destination already. It doesn't need to go anywhere. And the same thing for vertex F, because vertex F is also a destination already. It does not need an edge of any kind to get to a destination. So we have now discovered the shortest paths of every vertex to the closest destination. So is that helping? I mean, you kind of want to do this, with a different graph, by yourself, which is going to be your homework assignment. But that's the general idea of the Dijkstra's algorithm. Are we good so far? Yep.
Represent G prime.
So G prime is, so if you want to represent G prime, which is the solution graph, so G prime is really the same thing as using V as the set of all the vertices, except we use E prime as the set of all the edges, and that's it. That would be the solution graph.
Oh, okay. So it just shows it just draws another graph, I guess.
Yeah. Yeah, I think there's I cannot remember how to do it, but in Mermaid, you can use different lines, so like a dotted line. So I can change some of the lines into dotted lines, and that would represent a subgraph, okay, a sub-portion of the graph that we looked at earlier, but that would represent the shortest paths from every vertex to the closest destination. Yep. Are we doing okay so far with Dijkstra's algorithm? Now remember, this one is slightly modified so that it can track multiple destinations, and it does find the shortest path from every vertex to the closest destination. The modification is very, very small compared to the original Dijkstra's algorithm. And I figured, hey, with such a small modification, we can now find all the shortest paths of all the vertices. Why not? Right? It's kind of like a cheap, enhancement. So the next question is, well, if there's Dijkstra's algorithm, why do we need A-star algorithm? Because they do about the same thing, even though the mechanisms are different. So in order to explain that, okay, so I don't think we need this diagram anymore. Can I take it out? Okay. So in order to understand why we need the A-star algorithm, let's look at the map of, let's go to Kansas as a state. So we want to go to maps and then zoom out. I choose Kansas because it is in the middle of the entire United States. Okay, so let's just say that we want to go from a particular place in Kansas. Yes, we are in Kansas. I did not know Kansas City is so far away from the center of Kansas. That is kind of funny. It's not even in Kansas. So shouldn't they call it almost Kansas City? That is funny. Kansas City is not in Kansas.
There's a couple cities like that where they're not in their
Name.
states.
What it seems to imply. I can totally see all the memes in Kansas City, like we are not in Kansas anymore. Okay, let's say we are in Salina. Yep, Salina. Yep. Okay, so let's say we're here and we're trying to get to San Francisco. Okay, and we're using every single piece of street or road between intersection is an edge. Okay, obviously there will be a lot of edges between Salina or downtown Salina and San Francisco. But nonetheless, it is representable. Okay, we can represent all that stuff. So in this case, how long do you think it will take to actually, the other way around is even better. We're trying to go from San Francisco to Salina. So when you run Dijkstra's algorithm, what do you think it's going to do? If I were to plot, okay, graphically plot the Q, the set Q, okay, it has one single destination, which is Salina. All I really care is how do I go from San Francisco all the way over there to Salina. But Dijkstra's algorithm expands in a circular fashion. It is basically what we call a breadth first search as opposed to a depth first search, and it's uninformed. In other words, all it's going to do is to start with downtown Salina, and then we go like, okay, I'm going to look one intersection away from the center of the town, and those would become the next set of Q, right? And then it will go like 2 intersections away, 3 intersections away, and so on. So that means, the way graphically, if I want to look at the set Q, it will be the boundary of a circle that is expanding with Salina as the center, more or less. Is that okay? So that means in the attempt to find the shortest path from San Francisco to Salina, we will also find the shortest path from St. Louis to Salina. We'll then find the shortest path from Indianapolis to Selena, Cincinnati to Selena, and so on. Because we are basically expanding that circle that is centered at Selena. And we're just expanding that circle all the way until we have hit all the cities. You go like, that doesn't seem reasonable, okay? Because Cincinnati is in the wrong direction. I mean, sometimes I can understand that you can take a little detour and it ends up to be faster, but not that kind of a detour. Right? So that means, the Dijkstra's algorithm is, even though it is correct, it's not very optimal. Okay, and some of you are going to say, but Tech, that's because of your modification to Dijkstra's algorithm. What if we don't do that Dijkstra's modification? It's still the same thing. It's just that the concentric circle is starting from the origin instead of the destination. You're still expanding, concentric circles until you get to the destination. Yep.
So wouldn't that still work out well if we had like, for instance, portals, right? So if there was a portal in Indianapolis,
Yes.
then it would work out better.
Yes.
Okay.
Now, if there is a portal, as in the game portal, right, from Cincinnati or Indianapolis, all the way to San Francisco, the Dijkstra's algorithm will find that and say, yep, it is actually shorter to drive all the way east, and then it will just teleport you to San Francisco. It will find it, okay? But in general, with maps and physical locations, that doesn't work, right? So now, and remember what I said, it's not because of my modification to Dijkstra's algorithm, because with the original Dijkstra's algorithm, all we have to do is to reverse the destination versus the origin. And now the concentric circles will be centering around the origin, but it's still expanding in circles, and it's still wasting a lot of resources because it's going to explore vertices that really have no chance of being on the shortest path. All right, so you go like, okay, so how do we make this better? I mean, if you use common sense, right, you just go like, if this is where we are starting in the middle of Kansas, maybe we only have to explore up to maybe around here. Okay, maybe there's a shorter path by going backward a little bit and out of the way, but we don't have to go all the way back here. That's because of physical distances, right? So A star is what we call a heuristic algorithm. It uses a heuristic function to give you an idea of, does that make sense? Is that a good idea? Okay. So in this case, the heuristic function is a easy to compute function that will give you a not overestimate of the distance between two vertices. Okay, let me explain that. Okay, so what is a heuristic function that we can use in a map? Okay, so let me shift the map just a little bit so I can illustrate it. All right, there we go. So we can just draw a straight line, okay? Say from Tucson to San Francisco, okay? So that straight line, we can measure the distance, whether you want to take into consideration that the Earth is a sphere and look at the actual curve instead of the real straight line, doesn't matter. Because the actual shortest path is not going to be that short. So your heuristic function, which is very easy to compute because all you need is the GPS location of the 2 points, right? And then you can just plug it into some equation, and then out comes a very quick estimate of the distance. But that's always going to be an underestimate in this case, because even if there is a highway connecting from, what did I say? Tucson to San Francisco, it's not, at the best, it would be the same distance. But you still have, geographical features, mountains and whatnot, and sometimes you have to veer away from a lake and so on. So the actual driving distance is guaranteed to be longer. So that makes the heuristic admissible. Okay, so an admissible heuristic is a function that is guaranteed not to overestimate the actual length between 2 points.
Essentially, the rest.
It just cannot overestimate. Other than that, there are no other requirements of what a heuristic function needs to be. So that means if you're lazy, You can just say, can I just say the heuristic function is just 0 all the time? Be my guest. You have just degenerated A star algorithm into Dijkstra's algorithm by saying the heuristic function is always a 0. Which means, hey, it's still going to work. It's just that you're not benefiting from the A star algorithm. Now, in the case of a map, if you just use the physical distance between the straight line distance between 2 points as a heuristic function, it will help a great deal already. Because you might go back up a little bit from the middle of Kansas in our example, but it's not go past a certain point. It's not going to get past a certain point to the south. It's not going to get past a certain point to the north, because it is a relatively useful heuristic in this case to give you a realistic and yet not overestimate of the actual distance. Does that make sense? So that is how A star and Dijkstra's algorithm differ. That's the inclusion of a heuristic function is what makes the A star algorithm potentially a lot more efficient. Now, I said potential because I can invent a particular heuristic function to trick the A star algorithm to explore vertices as unnecessarily as possible. Okay, so yes, you can still construct a scenario where it doesn't help much, but generally speaking, if you have a reasonable heuristic function, then A star algorithm is going to be much more efficient compared to Dijkstra's algorithm. Are we still do okay? We are 5 minutes away from 1:20, so I'm not going to talk about the A star algorithm today. You should read it before Wednesday, because that's what we're going to do on Wednesday, which is kind of the same thing that we did today, except to the A star algorithm. I will have to give you the heuristic function and whatnot. But the question I really want to ask now is, why are we interested in finding shortest paths? Map is one, but are there any other scenarios where we want to find the shortest path between quote unquote 2 vertices? And by the way, what are the vertices representing? Yeah, go ahead.
Okay, so isn't this like used in like programming artificial intelligence with like the different matrices and forgot what it's called, the neural networks. I'm trying to remember what it's called. They use different nodes and to fine tune the AI. They have to
use back propagation to fine tune the weights of the connections between the quote unquote neurons. So in that case, so if you think about all the data points, okay, I shouldn't say that. It's basically you're approximating the actual model, so that you come up with the right value from the function. That's how neural nets function in general. But this can relate to, yeah, go ahead.
right?
DNS. Oh, domain name server.
Yeah, like the
Routing.
finding the shortest path to resolving it. And then,
So you're talking about routing between 2 internet addresses.
yes.
Yep. So that's the job of a router, and TCP/IP has that as a component built into it. Yep.
It can also be like if you want to find fastest path in the CPU, the RAM.
Not so much that one, because that one is basically fixed. You can't really change that once the design is done. Yeah, go ahead.
Possibly in social media.
In what way? So what would be the vertices be representing in that case?
For instance, in Amazon, certain items and consumer purchases one, they would then be recommended different items that they will purchase.
That may not be a direct map to what we are representing here, because that one is kind of more like a clustering. You're basically looking at people who purchase this item, and then you're asking, is there a correlation with people who purchase those items and so on? So because what you can recommend is limited, right? That space of, you might also want to consider blah, blah, blah is limited. So you want to be able to prioritize. Yes, go ahead.
Chess solving algorithms, maybe?
Chess solving algorithms is not about the shortest path. It is about the path to victory or a path to certain victory, which is a little bit different. And because it's also an adversarial game, you can apply certain types of optimization. It's called alpha beta pruning. So when you get to a game theory class, as a upper division class or a graduate class, they will talk about alpha beta pruning, which is a really neat idea. But it's a little bit different. It's still an optimization problem, but it's a different nature. So I can give you one example. What if the vertices are representing what your program needs to do, like as in the C program, C++ program. And the individual vertices in between are representing, each edge is represented by an instruction. So there are multiple instruction sequences that can get the same thing done. The question is, which sequence is the shortest? Okay, so unless your C compiler has an option that says, dash scenic route, which means I will find the most obscure way to get this done, but it will be done correctly. Most of the time, we want it to be done as quickly as possible, right? So that means, between two things, this is the state where you're at. This is the state where you need to be. We want to find the shortest path, which in this case, each edge is represented by an instruction that can incrementally change the state to the next, state. But which sequence of instructions, which path can get you from one vertex to another vertex, that's what we try to ask. So it's an optimization problem. All right. So that's all the time that we have for today. So on Wednesday, we'll be talking about the A-star algorithm. So please study and read the algorithm. And later today, I will release the homework assignment for Dijkstra's algorithm because we just talked about it. So I hope that it's still fresh in your mind. And I'll try to resolve the spreadsheet so you guys can actually make use of that feature. All right. See you guys on Wednesday.